Okay, so here we're going to prove that the perpendicular bisectors of any triangle ABC, are concurrent. So concurrent means that they all meet at one point. So all meet at one point is what this word concurrent means. So basically, if you have some triangle ABC, we could go through some of the theory here. So I could have made it a little bit bigger, but let's see. We got triangle ABC, right? Now let's just consider the perpendicular bisector of side AB, right? That looks something like this. Or better yet, let's get a color here. So that looks something like this, right? And then let's look at the perpendicular bisector of side BC. And now what we need to prove is that the perpendicular bisector of side AC also meets at this point P, right? So we're just going to state some things here. We're going to say, let's see what we have. Well, we know that P, right, lies on the perpendicular bisector of AB. So the distance, right, if you look, and again, I'm just giving you theory, this length and this length have to be the same by perpendicular bisector theorem. Because if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints. And then similarly, we have here, right, these are the distances of the endpoints to BC, and P lies on the perpendicular bisector of segment BC, so then that means that these three must all be equal. But then if you notice, then you have AP congruent to CP by transitivity, and P is equidistant from the endpoints. So the perpendicular bisector converse says that if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector, and then you're done. You know for sure that P will lie on the perpendicular bisector of AC. So let's write this out. Let's maybe draw a bigger picture to make it more clear to us. So let's now just, let's make it a little bit nicer. Okay, and we got A, B, C, and again, okay, so the perpendicular bisectors of any two sides, right? Of any two sides of, let's say, AB and BC meet at P. Okay, so that looks something like this, right? We got, if I draw carefully here, let's say that this is the midpoint. Let's say this is, all right, so let's say that that's the perpendicular bisector of AB. And then now I'm gonna, try and do my best here, guessing something like that. And this is fine as well. Okay, so this is P. It doesn't have to land on AC. I think if it's a right triangle, it does, or some weird condition. But this is a weird case, but whatever. But it doesn't matter because we can still show the result, right? So the perpendicular bisectors of BC and AB meet at P. Okay, and then by perpendicular bisector theorem, right, we know that P is equidistant from these two distances must be the same, this and this. So PB by perpendicular bisector theorem, let's not say so, by perpendicular bisector theorem, right, we have that P is equidistant from the endpoints. So BP equals AP. Right, those two distances are equal. And, right, you have it that P lies on the perpendicular bisector of BC. And so you have PB equal to CP. right? Both of these follow from perpendicular bisector theorem, right? So then that means that these three lengths are all the same. But then that means that BP equals AP, and then BP equals CP, so AP equals CP by transitivity. Now, P is equidistant from the endpoints of AC, of the segment AC. So, by perpendicular bisector converse, the other direction, right, which says that if a point is equidistant from the endpoints, then the point lies on the perpendicular bisector. So by perpendicular bisector converse, P lies on perpendicular bisector of AC. And we have it that this point P is concurrent. So all perpendicular bisectors meet at P. And this picture isn't the best one because the perpendicular bisector of AC looks like that, right? With it like being exactly like this. I think, I don't know what the condition is for when you have it where the point P, you could look it up, but I think it's that it might be that it's a right triangle or something like that, but whatever. Sometimes the point of concurrency in the triangle is on one of the sides, like in this triangle that I happen to have drawn. It looks close if I did this drawing well. But yeah, but all the perpendicular bisectors meet at P, so they're concurrent. That's the word. And we're done. And you could draw a more general picture if you don't like that special situation